Hello, this is Parag Juice. Welcome to Tech Capsule. Today we are going to study about the operation of a diode. A diode is a base unit which is used for switching purposes. It can be called as a simplest of the switch. The diode unit basically has two terminals, which is the anode as well as the cathode terminal. The anode terminal will be connected to the positive and cathode terminal will be connected to the negative of a power supply. Diode is used in majority of applications like rectifiers, inverters and all. So diode is represented like this in a symbol where you have the anode at one end and a cathode at the other end. The diode is made up of a base material which is called as a semiconductor. Now what is this semiconductor? When you look at the type of materials, we can see that materials are classified into three types, that is conductors, semiconductors and insulators. Conductors are those which are easy to conduct. Semiconductors are those which will be at a between condition for as compared to insulators and conductors. Insulators will be finding it difficult to conduct. Now, what is this conduction? When you talk about conduction in electrical systems, we are going to talk about energy bands or energy gaps. We know that there will be division of electron, or the electron will be divided based on the energy level into two areas. One is known as the valence band, where we have the electrons represented, and then we have the conduction band. Now what do you mean by valence band and conduction band? For example, I have an atom or I have a material which has an atomic number of 287. So here we can see the atomic number is 287, that is 17. So when we divide or when we represent the orbitals as well as the revolution of electrons, we can see that we'll be representing it like this. So here the electron division will be such that there will be 2 electrons on the inner orbital, there will be 8 electrons on the outer orbital, and there will be 7 electrons in the outermost orbital. Now, we all know that for an electron or for an atom to attain stability, it has the stability number 288. So if there is an one electron given to this, then the atom will become stable. Now in such a scenario, can we think of removing one of the atoms, one of the electrons from the outer orbital? That means we want to remove one electron from outer orbital. Now if we have to do that, then that would not be easy, because the electrons will be attracted towards the central nucleus with a very high force, because it attains stability at 288. So now to remove one electron from that, it would be very difficult. So that is why we can see that these electrons which are in the valence band, that is the outer ring electrons, is the valence band electrons. So we can see that there will be 7 electrons here in the valence band. Now what does it mean, or what does conduction band mean, and what does valence band mean? Here we can see that these electrons which are on the outermost orbital is called as the valence band electrons. Now what does it mean to be in the conduction band? In the conduction band, it basically means to have this electron released for conduction, so that it is free, it can move around. So this is not possible for an atom like this, where you have 287 atomic number representation, because it is actually going to attain stability by adding one more electron. So we cannot have this electron or one electron from that released, so that it becomes 286. So therefore what happens is the nucleus will be attracting this electron very much towards it, and therefore it will require a very high energy to have this electron released. That is, we have to release it from this valence band to conduction band, which is actually the free motion of electrons. So that is why this energy gap plays a very important role in the operation. So if I want this electron to be released to the conduction band, I should exert a large amount of energy to this. So this is known as the energy gap. So based on the width of the energy gap or the height of the energy gap, the materials are classified. If this energy gap is very high, like in this case where I have to remove the electron from a 287 atom so that it is removed from valence band to conduction band, then the energy gap would be very high. But on the contrary, if I have a situation where I have an atom which is represented having an atomic number of 281, so here we can see that the representation will be something like this. Two electrons in the inner orbital, eight electrons in the middle orbital, and one electron in the outer orbital. Now in this scenario, since the stability is at 2, 8, this electron will be or can be easily removed from the system because the stability attainment is at 2, 8. So if I want, I can easily remove this electron from valence band, which is the outermost band, to conduction band, which is free motion of electron. So in that case, we can find that the energy gap will be very less. So a small amount of energy would be sufficient to move the electron from the valence band to conduction band. So such kind of materials will be called as conductors. So insulators are those which will have very high amount of energy gap and it would be difficult to remove a valence band electron to a conduction band. While in the case of a conductor, we can find that the electron would be easily movable from the valence band to the conduction band, or free motion. So in the case of a semiconductor, usually it will be such that it is on an average, the energy required would be on an average. So that would mean or indicate that you are looking at a atomic number of somewhere in middle of this. That is, here we have a 287 and here we have 281. So 284 would be the ideal candidate for becoming a semiconductor material, and that is true because we have silicon having an atomic number of 284. So if I want to release an electron or if I want to attract an electron, the force required will be almost the same. Coming to the diode operation, we can see that the diode operation would require a semiconductor material like silicon as the base substrate. Now this semiconductor material, which is silicon, will be doped. Now what is doping? Doping is the process of adding impurities. Now for example, as I told, silicon will have the atomic number 284. So if this wants to attain stability, there are two methods. One is it can give off 4 electrons or it can attract 4 electrons. So now what we do is I'm going to add 5 electrons into this. I'm going to add 5 electrons into this. So what does it become? It becomes 2881. 2881. So if you notice, we can see that this gives it stability, and then you have one free electron which can be easily moved from the valence band to conduction band, right, so that it attains stability. So this basically makes this semiconductor into a conductor because it can release an electron very easily. You don't require too much of energy to release that. The energy gap will be very less. So such kind of materials are called as semiconductors which have n-type property. That is, we have an excess of electrons, so this is known as an n-type semiconductor material or n-type material. So what I do is I'm going to add a pentavalent impurity into this. So when I do that, what happens? The silicon number becomes, or atomic number becomes 2881, and it becomes, or one region of it becomes a n-type material. Now, if I want to convert it into a p-type material, the second quad type, so there what we do is we'll be adding a trivalent impurity to this. So what did I do? I'm adding 3 electrons to this. This is a trivalent impurity. So when I add 3 electrons to this, what happens? The atomic number becomes 287. Now we have seen what is the property of this, right? So here this would act as an attractor. It for it to attain stability, that is 288, it somehow requires one electron, right? So it will try to attract electrons with a great force from around it. So that is why this is called as a p-type material, because it has a hole in it. That is, it has a hole which has to be filled by an electron which is freely moving. So it will be trying to attract that. So such kind of materials are called as p-type semiconductor materials. So now we have two materials. So what did we do? We took a silicon semiconductor wafer, right? And then we did pentavalent impurity doping to give us n-type material, and then we did trivalent impurity doping to give us p-type semiconductor material. So this combination of an n-type and p-type semiconductor material is called as a diode. So if you look at this, so here this would be the anode terminal and this would be the cathode terminal. So if you look at this, we can see that when you join these two materials together, that is a p-type and n-type semiconductor material. Now, what is excess in n? You have electrons which are excess in n. You have this one, right? So if there are a lot of n atoms or semiconductor n-type atoms there, then there will be a lot of free electrons there, right? But in the case of p-type material, we can see what is excess in that. You have holes excess in that. So when you join these two together, naturally what will happen? At the point of contact, somewhere here, at the point of contact, what will happen? This electron and hole can recombine. The electron and hole can join, right? Because they want to join there. So such a scenario creates an area here, which is called as a depletion layer. Which is called as a depletion layer. So this depletion layer basically is the region where you have the recombination of electrons and holes taking place in the PN junction diode, or this junction created will be naming the diode as a PN junction diode. Now we'll be analyzing the diode characteristics. To analyze the diode characteristics, we'll be using a DC source. So what I'm going to do is I'm going to connect the anode to a DC source. The anode will be connected to the positive of the DC source, while cathode will be connected to the negative of the DC source. This condition will do what? Let us analyze. Now here we can see the excess of elements which are available here is the hole, while here, that is in the N region, we'll have more of electrons. So naturally what would happen? When we have positive connected to hole, holes will have a positive nature because it doesn't have electrons, while electrons will be negative in nature, or this region will be negative in nature. So this negative terminal will repel negative, because we have already studied like forces repel each other, unlike forces attract. So here negative will repel these electrons and it will force these electrons to move across this junction. Now this junction, as we told, this would be the depletion layer, but it would be easy, or it would not be that easy for these electrons to move across, because there is something which is known as a barrier potential which is created in between this. So this barrier potential, what it means is, the barrier potential is some kind of a hindrance. So assume it is a door. Okay, we have a door here. Now what should happen? The door is closed, but it is not locked. Okay, now if this electron wants to move across this junction and reach the P region, what should happen? The electron will be applying a force to this. Okay, so that force can be called as a potential. So when we have these electrons applying a potential onto this door will be, since it is locked or since it is closed, it will have a barrier potential. It would have some kind of force which is holding it closed. So when this electron exerts a force on this, the force will at a point of time cause the door to open up. So that is when the potential becomes greater than the barrier potential that you open the door. Same way here we can see the electrons will at a point of time overcome this and move into that. That would be based on the potential of the material used. So in case of silicon, it will be around 0.7 volt. So if the voltage developed by the electrons, potential difference developed by the electrons at this junction becomes greater than 0.7 volt, then this barrier potential will be overcome and the door will open and the electrons will move into the P region. Okay, so here we can see the electrons will be repelled by the negative terminal of the battery and the electrons will be trying to move across. It becomes over 0.7 volt and it moves into the P region, and then it would reach to the positive terminal. So this is how actually electricity flows or electron flow happens. So by convention, we'll be considering the current flow to be opposite in direction, that is from positive terminal to the negative terminal of the battery. But actually the electron flow is from the cathode to the anode, that is in the opposite direction. So this conduction or this process is called as forward conduction operation. Forward conduction operation. Now if you look at the characteristics, we can see that we'll be plotting the characteristics between voltage and current. So this is your forward voltage and this is your forward current, and this one will be called as the forward bias characteristic region. Forward bias region. So here we can see the characteristic would be something like this. It initially increases slightly and then there will be a sharp shoot off. This is because this will be the point where our voltage becomes 0.7 volt or greater. So once the barrier potential is crossed, then there will be immediate conduction of electrons happening, and that is why it conducts very fast. So you can see there is an exponential increase in current with a small increase in voltage beyond the barrier potential. Now what happens if I reverse the battery source? So here we can see I'll be trying to connect the negative to the anode and the positive to the cathode. In such a scenario, what would happen? Here we have the holes as the axis and here we have the electrons as the axis. So in this scenario, we can see the unlike poles will attract. So electron will be attracted by the positive terminal of the battery, and therefore the electron will be moving like this towards this, to the positive terminal. So here the electrons are not trying to cross over this barrier potential, because if it is trying to cross over the barrier potential, then only conduction will start. But here it is not trying because it has a positive polarity here, so it would tend to move towards that. Same way, the electron supplied from here will also be coming here and it will be joining into the holes of the P region. So we can see that there is no crossing over happening at the depletion layer. So this kind of arrangement is known as a reverse bias condition. This kind of arrangement is called as a reverse bias condition. So when we look at the characteristic of this, we can see that the characteristic will be something like this, where we have the conduction happening very slowly and then it suddenly shoots off. This shoot off happens because of a phenomenon called as breakdown operation, or this voltage will be known as breakdown voltage, VB. So this is basically the point where, due to this kind of motion of electrons, the depletion layer breaks down and therefore after that there will be free conduction of electron. So this is actually a very bad condition because it is actually damaging the diode. So we'll be trying to not operate the diode in reverse bias condition because it can damage the diode. So diodes are only used for forward bias operation, where we have the current flow in the forward direction. So that's it guys, that's all about the diode characteristics. So we'll be meeting with subsequent topics in the next modules. So please subscribe if you like the capsule and join me for such exciting capsules. Thank you.